This video is an attempt to add some comfortability to you taking your first final exam for AP Physics 1. It's kind of a mid-year update on all the things that are on the equation sheet that we've used so far, where to find it, so that way you're not searching for things on your first final exam. On the front side, the top box has constants and conversion factors, and in this box there's really just two things that we've used so far. The rest of it will come about later. The two things that we've touched on are the universal gravitational constant, capital letter G, and the acceleration due to gravity at Earth's surface, lowercase g. So the capital letter G makes its way into at least two of the equations that we've used so far. The first for gravitational force, and the second for one of our gravitational potential energy equations. And then, of course, the acceleration due to gravity, the acceleration that all objects have when they're released, when they're in free fall, lowercase letter g, which on Earth is 9.8 meters per second squared. The box below that contains a bunch of unit symbols, standard things that we really ought to know at this point. I'll caution you to say that about half of these we haven't really used that much. In the first column, we've talked about meters, kilograms, and seconds, but we haven't talked about amperes yet. In the second column, the only ones we've really used there are newtons and joules. In the third column, we've used watts for power, and I think that's about it. Some of those other units you might recognize, but we won't really use them until later in the year. The box on the bottom left includes prefixes, and I think I've emphasized this at this point, but on the AP Physics exam you really shouldn't expect to have to convert units very much. It's pretty rare, but sometimes when you're given a graph, the units might be slightly different, or maybe when they give you a number for something, there might be a slightly different unit. But I think almost always the units that you'll be given will be between kilo and milli. So can you convert from meters to centimeters, or centimeters to meters, grams to kilograms, kilograms to grams, seconds to milliseconds, milliseconds to seconds? If you aren't sure how to use those things, these prefixes, along with the factor by which you would need to multiply in order to convert the unit, are on the front page of the equation sheet. I've not really seen many examples, especially for first semester AP Physics 1 stuff, where you have anything that's much bigger than times 10 to the 3 or much smaller than times 10 to the negative 3. Then we have a box that lists values of trigonometric functions for common angles. Really, I think this is mostly here for people who, if you wanted to try and answer some of these questions without a calculator and you didn't know what the sine of 30 degrees or 53 degrees was, these are some answers to those common angles that they use on the exams. I think, honestly, the quickest thing for most of us will be to just use our calculators to plug in sine of whatever angle they want us to find in order to figure out what the answer is. But it does remind us that our calculators need to be in degrees. If we are given an angle in degrees and want to use that angle to find the trigonometric function, or if that makes its way into one of the equations that we're using. So make sure that if you are plugging in angles that are in degrees into your calculator, that your calculator is in degrees, not radians. Lastly, on the bottom, they have some conventions that are used in this exam. The one that applies to us most that I'd like to point out is that number 2 here, air resistance is negligible unless otherwise stated. So we've seen now that we've done several multiple choice and free response questions, that there are cases where air resistance is not negligible, and they ask you to evaluate some problem in that case. But any time where they don't say anything about the air resistance, we are supposed to assume that the air resistance is negligible. And so I think that with that information, I think that pretty much covers what's most important about the front side of the equation sheet. Then, of course, the back side of the equation sheet has all of the equations that we need to use to solve our problems, so we spend most of our time back here. The first 3 equations that we talked about were the kinematic equations. These equations are equations that relate the position velocity, acceleration, and time of an object. We use these for one-dimensional motion and for two-dimensional projectile motion, where we can, given a few variables, figure out where the object is going to be, what its acceleration will be at certain times. Just a few things I'd like to point out here. One, the top equation doesn't include position, and the bottom equation doesn't include time, which is an important thing when you're deciding which kinematic equation to use. Also, when we write kinematic equations, we could write them for the x direction or the y direction, but not both simultaneously. And anytime I plug in a velocity or plug in an acceleration, it has to be the acceleration in the x direction or the acceleration in the y direction. I can't plug in things that are at angles. And so in this unit, we spent a lot of time taking velocities that were at 45 degrees or 60 degrees and breaking them down into their x and y components to make sure that everything we put into the equation was for the x or y direction. Also, displacement, velocity, acceleration are all vectors, which means they could be positive or negative, and we need to be careful with the signs that we use when we're working with these equations. A lot of the time when we are using the kinematic equations, at least one of the terms will be zero. For example, when we use the middle equation to write an equation for the projectile motion of an object, for the horizontal direction, the last term will be zero because the acceleration in the x direction will be zero. Also, we often solve problems where the initial velocity of objects are zero, in which case some of these equations will be simplified. The next set of equations we have are the equations we used when we talked about forces, circular motion, and gravitation. Those equations include Newton's second law, our equation for friction, our equation for centripetal acceleration, and then a few which are much further down the list. Our equation for gravitational force, and our equation for gravitational field. So we'll talk about the ones at the top first. The first one is just Newton's second law. Most of the time, if we want to write it with not a lot of effort, we would put something like F equals ma, but really F is a vector, so it should have an arrow over it, and acceleration is a vector, so it should also have an arrow over it. And when we write F, what we really mean is the net force, and so we need to find the total force or net force that acts on an object in order to determine its acceleration. The equation below that is our equation for friction, which is F equals mu times n. And I think that, while they write the equation much differently, the way that we've understood the equation, there's nothing wrong with that. As long as you know the relationship between the three variables, that the force of friction is equal to the coefficient of friction, whether it be static or kinetic, times the normal force, then I think you'll be set. As long as you know there's two different kinds of friction, static and kinetic, and that there are relationships between what the object is doing, what forces are applied, and whether that object is at rest or sliding. The equation below that is for centripetal acceleration. We know that objects that are in uniform circular motion, traveling at a constant speed tangent to some circle, will experience a centripetal acceleration that points towards the center of the circle. Centripetal means center-seeking, and that center-seeking acceleration depends on the speed that it's traveling squared and the radius of the circle that it's traveling along. And then down below we have our equation for gravitational force, which is G times the product of two masses divided by r squared. So it's an inverse square law for the gravitational force, which depends on the product of the two masses as well. And this is for any two objects, not just large objects like the Earth. Although what we found is that since the gravitational constant, capital letter G, is such a small number that we really only get some appreciable force if one of the masses is very large. And then below that, we have our equation for gravitational field, which is defined as the force of gravity per unit mass. So the force of gravity divided by mass tells us the strength of the gravitational field. And that could be measured in meters per second squared or newtons per kilogram. And the way that we typically wrote this is just F equals mg. The weight of objects, W or F, is given by mass times gravity. After our kinematics and dynamics, circular motion, and gravitation units, we talked about energy, and there are quite a few equations that come from that unit. We have our equation for kinetic energy, our equation which relates energy and work, the power equation, and then several which are further down the list here. We have our equation for gravitational potential energy, both our equation which includes the gravitational field strength and the one that doesn't, for cases where you're much further away from a planet. And also our equation for elastic potential energy. And so all these equations came from our work, energy, and power unit. So first I'd like to talk about the different forms of energy. We have three different equations for potential energy. Gravitational potential energy, delta UG, a change in gravitational potential energy, is due to a change in height of an object. So delta Y. We wrote that a little bit differently. Typically, U equals mgh. The reason why they use deltas in this equation is because really the amount of gravitational potential energy that an object has cannot be well defined, or nor does it mean very much. What really matters are changes in gravitational potential energy, because we could define the gravitational potential energy to be zero at any point. And in fact, when we're solving problems, we do need to define where that's zero, otherwise we won't be able to solve the problem. But it's our free choice to decide where that zero line is for the height. Below that, our other equation for gravitational potential energy was defined such that the gravitational potential energy was zero at an infinite distance away from an object, which means that as I get closer, then the gravitational potential energy needs to be defined as being negative, because we want the gravitational potential energy to increase as two objects get further apart. And as we've seen, due to any two objects in a system, there is gravitational potential energy associated with their configuration if they're separated by a certain distance r. And so if we have three objects in a system, for example, there is a negative amount of gravitational potential energy due to each pair of the objects in that system. Moving on now, on the left, we have our equation for elastic potential energy, which is much easier to understand. Objects that are elastic, objects that can be stretched or compressed, have a certain spring constant, K, which describes how stretchy the object is. And if it's stretched or compressed a distance x, then it has some energy stored in it. And that is given by 1/2 kx squared. Moving back up to the top, one of the first types of energy that we talked about was kinetic energy, which is given by 1/2 mv squared. If the speed of an object doubles, then its kinetic energy will be 4 times as big. And then we have our two equations, which is where all of these different forms of energy typically get put into in order to understand a problem. And so we have the first, which says delta E equals W. We know that that W stands for the work done by non-conservative forces. So when things like friction act on an object, the energy can change, delta E. If the work done by non-conservative forces is 0, then delta E equals W, which means the initial energy is equal to the final energy. And that's where a lot of our problems are done. We'll equate the initial kinetic energy to the final potential energy of an object, or vice versa, or some other variation of that. We also know that the work done on an object is equal to the force that is exerted on the object times the distance that force is exerted over. And we need to know that the force that we need to use in that equation is the force that's parallel to the direction that the object is moving. So in the same direction, or 180 degrees away from that same direction for cases like friction. In any case, we can use the expression FD cosine theta to make sure that we're using the correct force. Underneath that, we have our equation for power, which is change in energy divided by time. Power is the rate at which energy is used or transformed or expended by an object. So delta E could be delta U, it could be delta K. If I'm pedaling to go faster on my bike, it could be delta K. If I'm running up a staircase, it could be delta U. And we could figure out, you know, the rate at which energy is being used up or transformed, because power, which is measured in watts, is energy divided by time, or joules per second. It's a rate. There's one equation that I kind of left out when I was going over the forces equations, and that is our equation for Hooke's law. If I stretch a spring by a certain amount, x, then there are certain types of objects that will have a linear relationship between the force that's applied and the displacement of the spring, and that tells us what the spring constant of that object is. The last unit that we covered was our momentum unit, and in that unit we really have two main equations. We have our equation for momentum, which says P equals mv, and we have our equation for impulse, which is that a change in momentum or impulse is equal to force times a change in time. Momentum on this equation sheet is shown as a vector because it's equal to mass times velocity, which is also a vector. And then a change in momentum, delta P, which is impulse, is given by force times time, because when a force acts on an object, for example, when a ball collides with a wall, it collides with that wall for a certain amount of time, delta T, and there's a force exerted on the object from the wall, F. And so if we know what that average force is, then we can figure out what the change in momentum of the ball would be. I think that just about covers all of the equations that we've used this semester, although there's one more that I want to point out. At the very bottom of the first column, there's an equation, rho equals mass divided by volume, which is the equation for density. Sometimes in AP questions, they will use the density in volume just to describe the mass of an object. It's very common. So if you're ever given if you're ever given the density and volume of an object, you should know that you should be able to multiply those two things together to have an expression for the mass. And the mass is something that makes its way into many of the equations that we have this semester. And so, it's one way where they add a little extra step to the problem to make it a little bit more challenging. Other than that, I think we've just about covered everything we've used. So with that, I would like to just point out that all these equations here, while they are very important, we've not talked about them yet this semester. And these equations here, same thing goes for them. We'll be talking about all those equations in our second semester, most of them right when we come back after break. The electricity section will be the last thing we cover before our AP exam, and waves will come next semester as well. The geometry and trigonometry section is something that we can never really cross off, because kind of like the density equation, there are many problems where there's an extra added layer of difficulty to the problem because you need to know the area of a rectangle or a triangle or a circle, or maybe you need to use different relationships of a right triangle like sine, cosine, and tangent. I hope that at this point you have that right triangle pretty much memorized, and you probably know most of the equations on the left as well. But they're there just to make sure that you have them, because a lot of the times, for example, when we're finding the area under a curve, or if we need to find how far someone ran if they're running on a circular track or something like that, then we might need to use one or more of these equations to figure stuff out like that. And so for that reason, you should always make sure that you're familiar with the equations that are in the geometry and trigonometry section. Lastly, I'll point out that we have this huge list here in each section of the equation sheet, which tell us all the different letters that are used in those equations. And these are like the defined quantities of our equation sheet. So capital letter E means energy, capital letter K means kinetic energy, capital letter P means power, capital W means work. So these are quantities which I think even when we're writing our free response questions, if you would like to use those symbols, for example, F to represent force, then you're able to do that. Or when you're writing equations, these are the symbols that you should be using and the words that you could be using when you're writing a response or when you're writing an equation. so that way everybody knows what you're talking about. If you start picking other letters, then we might not understand what you're trying to convey. Also, the reason why that list is important is because now that we have so many equations that we might need to use on the final exam, if there's any point where you know which equation you need to use, but you can't remember what one of the variables are, you could always look at the list that's there in order to remember what that was. As a final comment, I'll suggest that hopefully after this video you can put your equation sheet down in front of you and then look at that blank equation sheet and hopefully be able to find all the things that you need. And if you have any questions about anything that's on there, you need to ask me that before your final exam.